So we're now talking about studying pH, and first portion of the discussion is strong acid. As an example of a strong acid, we have a hydrochloric acid over here, and I'm showing what happens to HCl in water in two different ways. This is just a simplified version of it, dissociation producing hydrogen ion and chloride ion. This is the same reaction but in a more sophisticated way, which shows how HCl actually reacts with water, donates a proton to water. You probably already learned about Bronsted acids and bases, and you know that Bronsted acids are those that donate a proton. So that's what HCl is doing over here, produces hydronium ion and conjugate base, which is chloride ion. So the point to remember about strong acids is that they dissociate or split up in water completely, meaning 100%. So if you start with a certain number of HCl molecules, none of them will exist after a short while, and only ions such as hydronium ion and chloride will be present. And so talking about calculating pH for a strong acid, concentration of hydronium ion is expected to be equal to molarity of HCl that you started with. And then, of course, once you know hydronium ion concentration, you can find its pH by taking negative log of hydronium ion concentration. Let's consider an example. The solution of HCl we'll be starting our procedure with for this experiment is 0.1 moles per liter. And so, assuming all of the acid that was in this 0.1 moles per liter will be converted into hydronium ion, then hydronium ion's concentration will also be 0.1 moles per liter. And then if we take negative log of 0.1, we of course get 1. So what would theoretical pH be for a solution of 0.1 molar hydrochloric acid? The answer is pH would be expected to equal 1. Because again, negative log of 0.1 would be equal to 1. So the idea of this procedure is then to start with 0.1 molar HCl, which is what I'm going to do shortly, measure its pH, see if we can get a value somewhat close to 1. There is, of course, some sort of experimental error always involved, so we may get a value slightly different than exactly 1, but hopefully close to 1. And then progressively dilute this 0.1 molar HCl with water, each time decreasing its concentration tenfold. So then we're going to go from 0.1 to 0.01 molar HCl, and then to 0.001 molar HCl, and so on. So what about a weak acid in contrast to a strong acid? The weak acid that we're looking at here to contrast and compare with hydrochloric acid is acetic acid. Acetic acid's formula can be written as HC2H3O2. This is what this particular chapter in your lab manual uses, so I use the same way of expressing concentration. I'd like to remind you though that formula for acetic acid can also be written as CH3COOH. So these two formulas represent the same exact substance, it's just different way of writing this. I think the reason being, here it's kind of weird to have a hydrogen on the end of the formula, because remember, for any acid, it's expected to have H at the beginning of its chemical formula, so hence such a representation for acetic acid. So here, the molecule of acetic acid would be reacting with water. Again, Bronsted theory, acid donates a proton to the base. So water is actually acting as a base here, and when hydrogen ion is transferred from acetic acid to water, you get acetate ion, which is a conjugate base of acetic acid, and you get a hydronium ion. So what's the difference between this reaction for acetic acid with the one we looked at before for hydrochloric acid? Well, if you've been paying attention, you might spot one important difference in the way I wrote this equation as opposed to the first equation for HCl we looked at. Let me bring the previous screen back. So seemingly the same type of interaction. So acid donating a proton to water, generating hydronium ion, but there is one very important difference. Look at this. Arrow going one way only. So this is not a reversible reaction. You have complete transformation of reactants to products. There is no undissociated HCl left here. Compare that with this equation. So now I have two arrows going back and forth. It's seemingly a very minor detail, but there is a huge amount of meaning in it. Because this time you're showing that not all of the acetic acid is going to exist as acetate and hydronium ion. Instead, there will be some sort of equilibrium reached between undissociated acid and water and acetate and hydronium ion. And in fact, we can write an expression for Ka, which is an equilibrium constant expression for acid dissociation. As you know, equilibrium constant is written as concentration of products at equilibrium divided by concentration of reactants at equilibrium. So for Ka of acetic acid, the expression will contain equilibrium concentration of first product, which is acetate, times concentration of the second product, which is hydronium ion, divided by equilibrium concentration of acetic acid. You will notice, of course, that water is not included in the expression in Ka, although water, of course, is a reactant. So why would water not be included? Well, hopefully you know from lecture that because water is a solvent, there's very large amount of water molecules around. And so concentration of water is considered to be constant throughout all of this, and therefore water is not included. But what I wanted to emphasize here is that if Ka value is found in literature, it's something you can easily look up in a special table that lists values for Ka for various weak acids. The value you would find would be 1.8 times 10 to the negative fifth. So think about it. Look how small that value is. It's negative fifth. So what does it tell us? Well, it tells us that because equilibrium constant is so much small, so far below 1, it means that in this type of equilibrium, the reactants are actually favored. In other words, concentration of reactants is far higher than concentration of products, and that creates such a small value here. And so in this equilibrium, what would be the species predominantly present in solution? It would not be acetate or hydronium ion. Instead, it would be undissociated acetic acid and water. What does that mean? Well, it means that in fact, in acetic acid solution, unlike HCl solution, there's only a tiny fraction of molecules that do produce acetate and hydronium ion. Vast majority of acetic acid molecules will stay undissociated. And so equilibrium, as we say, favors the reactant here, meaning a major portion of the solution is major species in solution is undissociated acetic acid. So let's consider how we can calculate hydronium ion concentration here. So if we have the expression for Ka and we know the value for Ka, concentration of hydronium ion can easily be found by first assuming that because acetate and hydronium ion are produced in 1-to-1 ratio, concentration of hydronium ion and acetate will be equal to each other. And hence we can replace acetate with hydronium ion, giving us the following expression for Ka. So now we have, instead of acetate times hydronium ion, we have hydronium ion squared divided by concentration of acetic acid. So let's consider a 0.1 molar solution of acetic acid. How can we find its pH? Again, Ka for acetic acid is known at 1.8 times 10 to the negative fifth. because Ka is equal to hydronium ion squared divided by 0.1. Now, where did I get this 0.1? Well, this is the original concentration of hydronium ion, acetic acid. Now, if you were to write an ice table like you probably do for equilibrium problems, you would have to put 0.1 minus x here. X would represent the fraction of the molecules that actually broke up into ions, but we're going to assume that x is very, very small, because remember, only tiny fraction of the molecules actually dissociate. So we're going to assume that the equilibrium concentration of acetic acid is equal to the concentration of acetic acid that we started with, the original concentration. And so that makes life easier, because if we had minus x here, we would have to then solve a quadratic equation. But we don't want to, so we just put 0.1 here. And so mathematically then, hydronium ion concentration can be found as square root of Ka times 0.1. So I put numerical value for Ka right here, and I did the math, which you can of course check and see if you can get the same answer. It's probably a good idea to make sure you can follow along and get the same answer as I did. And so what you get here is the expected concentration of hydronium ion would be 0.0013 moles per liter. Now think about it. We're talking about hydronium ion concentration in 0.1 molar acid solution. But because the acid is so weak, the concentration of hydronium ion is much lower than concentration of hydronium ion in HCl of the same concentration. If you recall, for strong acid, we just said, well, it dissociates completely, so concentration of hydronium ion would be equal to concentration of HCl, so it would be 0.1. Here, it's about 100 times less than what we had in the strong acid. So same concentration of the acid to start, but because this is such a weak acid, the concentration of hydronium ion in the weak acid solution would be significantly lower compared to that of a strong acid solution of the same concentration. So then, of course, we can find the pH of this solution by taking negative log of hydronium ion concentration. So negative log of 0.0013 comes out to about 2.87. So what does this tell us? Well, again, let's contrast this with the strong acid. For the strong acid, expected pH for 0.1 molar solution was 1. This one is 2.87, or roughly 3. So pH is 2 pH units higher for weak acid compared to strong acid of the same concentration. So what I summarized here is I wrote pH of a weak acid of a given concentration is always higher than the pH of a strong acid of the same concentration. Remember, higher pH means lower concentration of hydronium ion. So this emphasizes that weak acid has a lot fewer hydronium ions compared to a strong acid. Now, the question I usually get at this point in class, if you guys were here, maybe somebody would have asked, okay, that's all fine, but how do you know, if you're looking at the formula of a given acid, whether the acid is going to be weak or strong? The answer is pretty simple, really. In fact, there are very few of truly strong acids that exist in nature. And what I did here is I gave you a short list, which if you memorize will help you down the road for organic chemistry, for biochemistry, for any kind of chemistry courses you take. I only included 4, so it's not that hard to memorize. So these are truly strong acids. They include hydrochloric acid, HCl, nitric acid, HNO3, sulfuric acid, H2SO4, and perchloric acid, HClO4. Sometimes also iodic acid, HI, is included, but these are the 4 that I think you will probably see the most. All other acids that exist in nature are considered weak. So unless you're looking at a formula of an acid that's not one of these 4, you can assume with pretty good degree of confidence that you're talking about a weak acid. One exception here I'd like to mention briefly is phosphoric acid, H3PO4. That one is sort of in a class of its own because it's considered medium strength. All other ones, with the exception of these, would be considered weak. So in our next video, we're actually going to take a look at data and how you're going to fill out your data sheet. That's all for this one.